Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm going to maybe start things rolling. We had some questions earlier this morning about the control questions, and we kind of deferred to this later this evening. What do you see as some of the challenges for the kinds of approaches that you've been looking at? And especially the thing that I'm worried about is the number of training samples you can get with the robot is always going to be very small.
Sure. So I think there are a couple of questions in there. I think one of them is that the exploration right now is very, very slow still, I think. So being more sample efficient most likely would require different representations for the action space, something hierarchical as opposed to what's typically being used right now, which is hierarchical on the input, but not hierarchical on the action space. Another related kind of line of work that I think will be very relevant is the work on domain adaptation, where in Vision there's a lot of work already on you learn in one domain, you make it applicable to another domain, and so the question is, can you do similar things for control, where simulation is much easier to come by than real experiments, and so can you learn to adapt quickly beyond just fine-tuning, but have a strategy for adaptation that could be used to learn more quickly on a real system.
Okay, so my question is for Peter. So in the last talk, one key ingredient was the multi-scale approach. The fact that in that case, you start from a very low resolution thing, and then slowly you get the details. Do you think it's possible to do something like that for reinforcement learning for the problem that you are tackling, where to use something hierarchical where you look at different time scales?
So yes, I think the last presentation was, in some sense, kind of sketching an idea that at the abstract level I think is absolutely applicable to action, except that it's maybe not immediately clear how to make it into real actions as opposed to outputting images. But so I think if there's a way to output abstract actions, which would be likely sit in memory in some sense, which in turn would then output the lower level and yet lower level actions, I think if somebody can make progress on that, it'll probably require more than one paper, but if there could be a series of papers making progress on that, I think that would go a long way in advancing the ability to learn more quickly for action.
We have a question over there.
Hi there, thanks for your talks. To what extent are deep methods state-of-the-art across NLP?
Across NLP? Well, they're very popular in NLP, and they are clearly state-of-the-art in language modeling, and now they're state-of-the-art in machine translation. They've been shown to be state-of-the-art on various tagging tasks. Maybe you have other things to add?
I think a relevant data point is that almost all of the papers that were published in the most recent NLP conferences use deep learning in some way.
Okay, thank you.
Hi, I have a kind of technical question. There are a lot of frameworks for deep learning computation now, Torch, Tiano, and many others. And it makes some kind of mess for researchers and developers. Did you consider creating one framework that will unite all these? I understand that it requires collaboration between different
first of all, it's
companies.
good to have diversity because different frameworks have different advantages. Some were meant to do more for research and more flexible, and others allow you to get results quickly on specific architectures, for example. We see some convergence towards using automatic differentiation or symbolic differentiation. So I think that this is an interesting direction. I think it's good to have diversity, but we'll see. Maybe TensorFlow will take over.
Well, diversity is good, but I see that the number of frameworks grows, like, I don't know, exponentially. So Maybe it's just not the time yet to collaborate, but someday.
But I mean, what would you do about it? I mean, you can't say you don't write in this framework, right? So unfortunately,
I don't, but my friend does. Okay, thank you.
Yeah.
This is, I think, one of the questions that was on the list on the website, but I thought it was a great one.
Can you speak closer to the microphone?
Sorry, hello.
Well, I think you can take it out of the...
I'll just stand like this, it's okay. One of the great questions that I saw listed on the website is what happens to unsupervised learning? Now, there was this brilliant talk here that probably not too many of us really understood, but it sounded great. But other than that, there was very little about unsupervised learning. Any thoughts?
I think unsupervised learning is very challenging, and it's back as a really exciting topic. I think it's been left a little bit for a few years, but what's exciting is that there are very different approaches that people are looking at, completely different training objectives and ways of thinking about the problem. It's kind of the Wild West right now. How should we do unsupervised learning? There's so many possible ways. Every year we get several new ideas on how to handle that. So,
You say language modeling is unsupervised.
Actually, can I respond to that?
yeah.
So with respect to language modeling being unsupervised learning, there is really something different about images and language, say, because language was meant to be understood. So it was designed. I mean, there really is supervision. So there's a really huge difference between, like, you want to understand the density of all image patches of size 32 by 32, and I want to understand which word is going to follow the next, because, and the problem with trying to model the density of image patches or whatever is it just hasn't been particularly successful. And there is lots of weak supervision. So it's sometimes hard to justify a fully unsupervised, approach when other things are working really quite well.
So another big difference is that language has a natural sequential structure where the joint probability can be decomposed into the product of the next word given the previous ones, and it's kind of a natural task. If you try to do the same thing with pixels, it works for MNIST, actually. It's called NAID, but it doesn't scale that well, probably because you really want to take higher-level decisions about the content of the image, and that's a more natural thing there. So the nature of the data, as Arthur is saying, is really different.
But there is a sequential structure in images. It's just coarse-defined.
Coarse-defined, but we don't observe. Well, I guess that's what the Laplacian thing is doing.
I think, like many of us up here and in the room, I'm very excited about unsupervised learning these days. I got started into it by the recent trend in method of moments-based learning in the machine learning community, but I think what we saw in the last year and a half in terms of recent advances in learning variational autoencoders and the like have opened up a wide range of doors for unsupervised learning and an incredible number of questions. So there are going to be a couple of workshops at NIPS where I hope we're going to get into the nitty-gritty details of these. But I think almost nothing is known now, conditioned on the recent advances. I hope every one of you in the room starts working on unsupervised learning.
Yeah, I mean, somehow it depends on what you count as unsupervised learning. So in general, prediction, if you're just predicting the next frame in a video, or if you're predicting the next frame of audio, or if you're doing text prediction, to me, these are all unsupervised. I mean, the distinction for me is whether or not a human had to come in and give labels that help you solve the problem. And maybe this is more like a pragmatic thing, because if it's unsupervised in that sense, it means you essentially have limitless data. But that doesn't answer. I mean, most of the prediction models, you're mostly just minimizing log loss. So there's a standard loss function there, which isn't the only loss function you can consider for unsupervised learning. So I feel like with unsupervised learning, the big question is always like, what is it that you're actually trying to optimize? And for me personally, as soon as you get away from optimizing just reproducing the data, it becomes very murky.
Oh, did you want to say something?
Well, one thing that made me particularly exciting about the supervised learning, even though I worked for 10 years on unsupervised representation learning, was the fact that the networks that have been trained on ImageNet actually generalize to new tasks to other data sets. And that's one of the motivations why you might want to study unsupervised learning, because you want to avoid overfitting on a particular data set and rather want to learn generally useful representations. And so I think what would be particularly exciting to see is, say that we test unsupervisedly learned models or semi-supervisedly learned models on ImageNet and see them transferring, or if they succeed on ImageNet, they are likely to transfer also to other data sets as we have seen in the past. And so a new benchmark could be that we fix the performance, we want to achieve, say, less than 10% error on ImageNet, but with less and less labeled data. That could be one way to approach unsupervised learning.
And there are many other types of data sets other than language or vision where unsupervised learning is particularly interesting. So for example, we do a lot of work with healthcare data where you might just have very noisy signals about what's going on with the patient coming from, let's say, billing codes or from laboratory test results. And one wants to try to learn, try to discover new subtypes of the disease, try to discover hidden trajectories through which patients' hidden state, clinical state is evolving over time. And deep learning can tremendously contribute to these unsupervised learning in completely new areas.
Let's go to the next question.
I had a question basically targeted at Peter. I mean, one of the hopes is unsupervised learning would be useful for RL, but you mentioned that you tried doing, this went by a bit quick, but you did some sort of unsupervised pre-training and it wasn't helping, and then you took a pre-trained DQN and it still didn't help. Can you elaborate?
Yes, that went a little quickly, but in a little more detail, what we were hoping was that training essentially dynamical systems models, but in pixel space in this case, or in an encoding space, thanks to some autoencoders or something like that, would result in representations that help learn a Q function more quickly, because you would hope that the things you need to extract from the image to predict the next frame would maybe be the same things that you need to extract to predict what action will be a good action. And that might be true, but it wasn't helping to train in parallel on prediction and training a DQN network. And so then at some point we decided to say, well, we don't really know even if we can hope this would work, even if we had a really great way of learning to predict frames. And so then we said, let's take it to the extreme. Let's pre-train DQN, a DQN network on a bunch of different games, of course, separate networks, until they're fully trained. Once they're fully trained, zap out the last layer, the weights there, re-randomize the weights there, and just train that layer, but feeding through everything that's been, so to say, perfectly trained ahead of time. And the learning curves that I was showing was comparing standard DQN, where you don't have anything in the initial layers but random, with where you just retrain the last one, retrain the last two, or not just retrain, but you also fine-tune the earlier ones. So that's why there were 4 curves that were our experiment, and then 1 curve, well, they're average over multiple runs, but 1 curve that's DQN. And so the finding there was that, at least in our experiments, that initializing with what ultimately needs to sit there didn't speed up the training at all. Now, what to conclude from that is not 100% clear, but it definitely made us conclude that focusing on improving our learning of video prediction to share that learning with Q network learning was not what we wanted to focus on. We wanted to think about, like, better understand what's going on there and why even that is not helping.
So this was for the same game, right? So this is totally bizarre. If I train on Space Invaders and I keep everything fixed except the last level is a linear function approximator. So you can use sort of off-the-shelf, good old-fashioned Q learning,
likely,
right?
likely part of what's happening, I mean, is that the initial Q values are pretty far off, and it's a self-supervisory algorithm, so it has some trouble. So it might be a matter of revising the Q learning algorithm to account for the fact that it is self-supervisory, and maybe once that's revised, it could learn more quickly that way. But kind of using it the standard DQN way wouldn't have it learn more quickly that way.
Oh, so you're still doing sort of the SGD objective even on the final layer. You didn't use a more classical.
No, we used the exact same objective that we would have used otherwise if we were training everything, which is the Bellman error objective.
Okay.
Okay, Mark.
My question relates to testing generative models. The way I see it, we have on one end of the spectrum testing maximum the likelihood on the generative distribution, but we see algorithms like NICE that achieve very, very good likelihood, but the samples don't look very well. And on the other hand, we see generative adversarial networks which create insanely good samples, but might be massively overfitting and just copying the training set. Do you have an idea of where a very good quantitative measure of testing generative models might arise from?
Yeah, so let me first start with the premise, because actually one of the points in Emily's talk, and you can also see it in Sumit's most recent paper, is if you take paths through the Z-space in the GAN, everything is different. She had the one slide where you kind of added a little bit of noise and do the thing, and you kind of look at the images. It is completely clear that you're not memorizing neighbors. And actually, for example, in Sumit's paper, what he did was you make a single pass through the data set with very small gradients. So one image can't possibly affect the final outcome that much.
I agree. Sorry.
So it's quite likely that the GAN is giving up on a huge part of the space, but it isn't memorizing. The second thing, but more to answer the general question of how should you evaluate these things. And sometimes I think this is one of the real problems with unsupervised learning by itself. You should have another task that you do it. I mean, what we should have is a huge bank of tasks. As he was saying, what's important, unsupervised learning is good when it lets you do the thing that you want to do. You shouldn't, I think log likelihood is actually, even when you say, oh, there's some models that give very good log likelihood, log likelihood isn't a canonical thing in that it depends on the representation of the input. You can change the representation of the input, and which models give better log likelihood gets completely flipped around. So there isn't any, the problem with unsupervised learning is there is, by definition, by some definition of unsupervised learning, there's not a good way of measuring it. You have to have other tasks that you use to measure it. You have to have outside signal that says, this thing was good for helping me solve this other task. Otherwise, you're going to be caught in morass.
One thing, I agree on what you said, and the experiments are awesome, but that's why I said quantitative measure of how to measure, for example, the fact that adversarial nets cover the whole distribution of what you're training on.
Maybe also one more comment. So we just published a note on arXiv where we also show that these general belief that the samples, the perceptual quality of the samples correspond to high likelihood, that is not true, right? So one just have to be aware that good samples can come with a bad likelihood or vice versa.
I found that within a single model, there's usually a good correlation between the log likelihood and the quality of the sample. It just doesn't transfer between models. Is that do you agree with
that's
that?
fair. Yes. One thing I want to add is you can think of the log likelihood as just measuring the KL divergence between the distribution of the data generating distribution as the reference and the distribution of the model. But there's another KL divergence, which is the other way around, which would also be minimized if they were equal. And that actually would behave differently than minimizing the, in particular, it would lend itself to picking some of the modes and not necessarily paying too much attention to all of the modes. This is more like what GAN does. And actually, in the GAN paper, we showed that what is being approximately optimized is something like a mixture between the two forms of the K divergence. That explains why we see sharper images. And we would also expect that normal log likelihood, if we were able to measure it, to be not so great.
So can you just comment on that a little bit further? So if you take the view of GAN in terms of being something very close to moment matching, where does that view come from?
Which view? You mean the KL thing?
Yeah.
Well, that came from a sort of game theoretical analysis, asymptotic analysis that relates the objective function to this Shannon divergence that is a mixture of the two, essentially, roughly a mixture of the two divergences.
Do you think that using that inverse KL to test generative models?
Oh, we can't measure it because we don't have the data generating distribution, and it's appearing inside the log, right? So we can't use the data for. So the GAN objective function is meant to be a proxy for that. Maybe we should go to the next question.
Hi. So you were mentioning earlier for unsupervised learning that one of the reasons that maybe one of the reasons it works well for natural language is that language is meant to be understood, or like kind of by definition has a structure to it that we should be able to find. Is there work?
Another reason is that we have a lot more data in language than in images, at least as far as how many we actually use right now.
Right.
We have a lot of, I mean,
well,
there are a lot of
maybe even. It also takes a lot of compute power to use all these images.
It does use a lot more compute power.
Sorry, go ahead.
So maybe that partly answers this, but I was wondering if that means that like unsupervised techniques would be well suited towards like music tasks.
Music, you said?
Music, yeah, because I don't see a lot of work here using deep learning on music, and I'm wondering if there's.
Oh, there's all the work on using LSTMs, for example, for generating music from Douglas Eck, like I don't know, 8 years ago or even more. There's been a few papers in that thread, but probably it's going to come back now that recurrent nets are really hot.
There's actually there's a problem with generating audio. It's kind of hard to represent audio.
Right, that was symbolic representation.
Yeah, so if you're using MIDI or something like that, it's easy. But if you want to represent natural speech the same way that we go straight to natural images. It's not so easy because you have to model phase, or you have to find some representation that the network can naturally represent. It seems to me that once that problem is solved, then we'll start doing a lot more audio generation.
Thank you.
Hello. I have a non-technical question that I'm curious about. So there's been a lot of very impressive work over the last few years for vision tasks, coming from many different universities, things like image recognition and seam labeling. So the thing I'm curious about is, so who is funding this research and why?
It's the FBI. I know the answer to that.
I mean,
Facebook.
Yeah. Facebook does fund some of this, and I mean, they fund me to do it.
Google clearly funds some of that.
I mean, NSF funds it. All the usual suspects.
Like, what are the problems they're funding you to solve?
Sorry? Who?
Like, what are they funding you for? Like, what are the problems they're funding
To
you
get an
solve?
extra few % on ImageNet.
Like, why? I'm not really curious. I'm just not really sure why they're funding that.
Well, there's also funding for basic research actually exists.
Okay, I mean, I guess I'm just curious what's the end goal. But fair enough. Thanks.
But maybe we should ask some of our computer vision friends what they think about this. I mean, faculty or getting grants and stuff and so on. I don't know. All right, next question.
Hi, question for Alex. So this general problem of learning an algorithm seems really, really hard because the space of simple algorithms is just ridiculously huge. And so I was somewhat surprised that your results were able to generalize. And so there must be something wrong with this intuition that the space of algorithm is just too huge and it's hopeless to do search on it. So I was hoping you could clarify why this intuition is wrong and why you're able to get some results in this area.
I think, to put it simply, it works because they're simple algorithms. So the space becomes huge because it's combinatorial, because there's lots of the sort of small algorithmic primitives that you can combine in different ways. And I think if you try to learn a complex algorithm in one shot that involves lots of different primitives, it's guaranteed to fail for that exact reason. So I think any serious approach, I mean, one thing I should say is it wasn't our long-term goal to learn more and more complicated algorithms with a neural network. After all, these are algorithms that are pretty straightforward to code. It was more to have a neural network that could sort of reason algorithmically and apply that to real life situations where you maybe don't need such complicated algorithms. But if you do want to get complicated algorithms, I think it's clear that you need something that builds them up step by step and transfers them or is able to store them in some way and reuse them.
So humans are able to learn, to learn to reason algorithmically, and it's probably not something that we were explicitly evolved for. It's only recently we started to program. So it's probably a side effect of the sort of normal kind of cognitive work that we do that turns out to be useful for these tasks. And humans aren't that great at doing it, but it gives us hope that neural nets will be able to do it with maybe a bit more tricks and computing power and so on.
I mean, humans are quite poor at algorithmic reasoning if they don't have, paper to write things down or computers to check things and so forth. And even if they do, often, yeah. So it's clearly not something that comes very naturally to us.
Thank you.
Enforcement line?
Hi. In RL, sometimes it's easy to learn policy than the Q functions. I wonder how that extends to the deep learning setting and whether it's easy to learn, let's say, deep Q functions or deep policies.
Sorry, any chance you could repeat that?
Yeah. In reinforcement learning, sometimes it's easy to learn a policy directly than, let's say, the Q function itself. And I wonder in the deep learning setting, when you do deep RL, if you could elaborate on this, if you have tried to learn, let's say, a deep policy or a deep Q value function.
Sure. Okay. First, a very simple kind of intuition why sometimes learning the policy could be more convenient than learning the Q function is because ultimately you want a policy, you want a prescription, or often that's what you want. You want to go from state to action. Let's say your action space is discrete. There are a few options there, right? Then if you learn a policy, you're focused on discriminating between those actions and deciding which one is the better action between the set of choices. Whereas if you try to fit a Q function, you're actually largely applying most of your fitting power to the overall value of each state-action pair, but you're not really zoning in so much on the difference between different actions in a given state. And so you might have a really good Q function fit overall that has relatively small errors, so to say, overall, but that actually has flipped values for optimal versus suboptimal action, but yet could still be somewhat close. And so you're kind of not, until your Bellman error essentially becomes 0, until that happens, you might actually still be pretty far away from picking the right action in some situations. In terms of why we, let's say, all of the DeepMind results were, at least initially, were with Q learning, and I think in my group, all the results we had initially were with policy search. And I think one of the reasons was that we just felt that the kind of research effort of working with policy search was easier. It was easier to understand that the policy is making progress than it was to understand whether the Q function was a better Q function than the one we had before. And so I think it wasn't so much that necessarily the policy representation was better than a Q function representation. It was more that us looking at what we're getting, it was easier to reason about what we get when we have a fixed policy versus a fixed Q function, and when we change it, how good that changes.
There's another advantage to learning policies, which is it generalizes to continuous action spaces in a more straightforward way.
Thank you.
Hi again. I have kind of general question. In your opinion, what will be the next big thing in learning hyperparameters for deep neural networks?
This should be the last two questions, by the way, because it's almost 9. For hyperparameters?
Learning hyperparameters.
Yeah. What will be the next? What is the future of this whole study?
Beyond Bayesian optimization? Or?
Deep Bayesian optimization.
Thank you.
I mean, something I would say is that most of the work in this area has been focusing on learning. Learning for one specific setup, the right exploring where experiments are for like one neural net where you explore the different hyperparameters. You only get a few, tens or hundreds of trials at most. Otherwise, you might as well do random sampling. So you can't gain a lot because you don't have space to learn a complicated policy, essentially. But if you are able to learn, like grad students do, through many architectures, many data sets, and generalize across these, then you could have tens of thousands of points of, this architecture for this data set with these hyperparameters give me this result. I think you'd have something more powerful. But of course, Gaussian processes there wouldn't work simply for computational reasons. You'd have to use something else.
Well, maybe if you push that a little bit further and think about extrapolating, right? So suppose you write down an architecture in Torch or Theano, and 100 layers deep. Could you hit a black box? Can you hit a button and then come up with a way of trying to extract out a much smaller model family automatically from that? Do the type of experimentation that Yoshi was talking about, and then learn how to generalize back to the one you actually cared about? That might be fun to explore.
I just wanted to refer to Ian Goodfellow's. I can't remember the first author. I apologize. Ian Goodfellow was one of the authors. It's ICLR submission. Do you remember the name?
What is it about?
But basically, it's basically what you guys are talking about. So it's how to take a net and grow it a little bit by replacing a unit with two units that are give the same output and then adding a little bit noise or adding an extra layer. I can't remember the name. But it really is a powerful technique for doing what you guys were saying. You can't get back down, but you can go back up. And the idea is you can start simple and grow bigger and bigger and bigger. And that's super powerful because effectively what you're doing is taking the optimization surface and blurring it. You're doing a multi-scale, over the optimization surface. And the bigger you make the model, the finer the details of the optimization surface are. So as a kind of method for hyperparameter search, what they have in that paper is it's really, I think, going to be useful.
Last question?
Okay. Just coming back to neural Turing machines, one challenge with learning algorithms is that you sort of either get it right or wrong, right? There's no intermediate algorithm that's correct, at least I think. So do you have a sense of how they manage to kind of build up the building blocks to get like something like copying to work?
Yeah, so it relates to having a kind of curriculum again. So even when in the first paper, we didn't have an explicit curriculum, but we always gave it a range. So it was copying sequences of length 1 to 10, right? So a certain fraction of the time, all it had to do was copy a single vector. And there, the supervision signal is very clear. And then it has to, from there it might start to learn 2 vectors or 3 vectors. And then at some point it learns a rule that generalizes. And actually the rule doesn't generalize perfectly. So that slide I showed where it generalized to length 120, there was actually a mistake somewhere after, 80 points or something like that. It misses one out and then does all the rest, which means that the log loss was actually very high. So when I first looked at the loss, I thought it was just failing on the long sequences. And it was only when I looked closely and realized that actually it would be, it would just have missed one line out or repeated one line. Does that make sense? So in a sense, it's true what you say. It had, the algorithm was either completely right or it was completely failing. Quantitatively, but qualitatively, I could see that it was almost successful.
I guess the problem is that you're trying to learn a procedure, I think. And so you either sort of have, ultimately, right? And so even if you learn how to copy, 3 letters, that doesn't seem like it would help you in learning the procedure unless you just learn the procedure.
What you'd want is to have a generic notion of what copying something means that you can reapply in different situations. And my feeling is that is possible. All of these things are ultimately encoded in the weights of the controller network, and we know that neural networks are quite good at generalizing and even transferring across tasks. But it's not. We certainly haven't explored that really. It certainly would be challenging.
All right, so we are at the end. Let's thank again our panelists, all our speakers. Thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.